The law of conservation of energy, G. An important law of the universe. Here's what it says. Energy is neither created nor destroyed. It can only be transformed from one type to another. This means that if you're looking at a closed system where there's no outside sources of energy, the total amount of energy at the start and the total amount of energy at the end must be the same. You want the short version? Energy has to come from somewhere. Just that phrase alone, Sheldon, is my fallback whenever somebody asks me is it possible physics question, especially about all the Marvel superheroes that are going on right now. Hey, I saw a movie where the Hulk was able to throw a car. Okay, I'm telling you, if he threw that car and he gave that car potential energy, that energy has to come from somewhere. And if it comes from the Hulk, he'd be eating 24/7. He wouldn't be able to be a superhero. He'd have to be stuffing himself all the time. I saw a movie where Magneto lifted the stadium up. Okay, he's giving that stadium potential energy. That energy has to come from somewhere. And if there is no energy source, I'm sorry, even if you could somehow manipulate magnetic fields, you still couldn't lift anything. You could not. In fact, we're so certain that the law of conservation of energy is correct that when we find something that appears to contradict the law of conservation of energy, we would rather change the universe than change the law. What's the energy of motion? What did we call it last day? Begins with the letter K. Okay, kinetic. We have known since the 1930s that the universe is expanding, but in 1998, we realized not only is the universe expanding, it's speeding up. If you're speeding up, what type of energy is that? The energy of motion. Kinetic. Somehow the universe is gaining kinetic energy. Rather than say the law of conservation of energy is wrong, we've said that energy's got to come from somewhere. We've given it a name. That's what we mean by dark energy. Dark energy is the placeholder. We know there is some mysterious energy source out there that is giving the universe kinetic energy, allowing it to speed up. And we're so certain that the law of conservation of energy is correct that we're willing to invent this stupid thing called dark energy as a placeholder rather than change the law. This also explains, for example, that machines have to have an energy source. This is why you can't have a perpetual motion machine or a machine that gives you more energy out than in. Energy has to come from somewhere. Energy is not either created nor destroyed. It may only be transformed from one form to another. The poetic way of saying this says that when the Big Bang occurred, the universe had this much energy, and it's always going to have this much energy, neither more nor less. The depressing part of that is it turns out that energy is going to want to spread out over the universe. Energy runs sort of downhill. Energy flows from high energy sources to low energy sources. And so billions, maybe trillions of years from now, the universe is going to end up with all of the energy spread out. And when you run the numbers, it means everywhere in the universe is going to be about 2 degrees Kelvin, and there's going to be no life or stars or anything. Preview of coming attractions. Have I mentioned you're going to die someday? You're going to die someday. Okay. That fact that the amount of energy remains constant, that it only gets transferred from one to another, allows us to do some fairly simple math. Both the kinetic energy and the potential energy of a block sliding down a ramp are shown below. Fill in the missing values. How much potential energy are we starting with? Don't know. But what's our initial speed if our kinetic energy is 0? 0, starting at rest. Oh, how much energy do I have at the bottom, grand total? Do the math in your head, please. 75 joules. You know how much energy I have to have here then? Same answer. 75 joules. You know how much energy I have to have here then? Same answer. 75 joules. You know how much energy I have to have here then? Same answer. You know what? It seems to me we must have started out with 75 joules of potential. If something starts to slide down, let's pretend this hill is made of ice so there's no friction. If something starts to slide downhill, what happens to its speed? Stays the same, speeds up, or slows down if it starts to slide downhill? What happens to its kinetic energy? Increases. So, now we have how many joules of kinetic energy on the second location? 25. It's speeding up. The only way it can speed up is if you lose potential. It's got to come from somewhere. We keep sliding down the hill. We speed up even more. We now have 50 joules of kinetic energy. How much potential energy do we have? And at the end, at the bottom, you end up with all kinetic, no potential. So in words, the law of conservation of energy, sometimes I'll abbreviate it as CV, says the amount of energy in a closed system never changes. As an equation, stored energy, initial, plus motion energy, initial, equals stored energy, final, plus motion energy, final. There's no way we're going to write that. We have symbols. What did we call stored energy? What did we call motion energy? Equals, something happens, you move downhill, you throw, something happens. That there is the law of conservation of energy, GG. Now, this stored energy, Andy, could be gravitational for height. That would be MGH. Or it could be, we looked at storing energy in a bow, work force times distance, stored energy. Okay. If we want to be even more accurate, we can finally start to include things like energy lost to heat and sound. We can say it this way. The initial potential plus the initial kinetic equals the final potential plus the final kinetic. But if the numbers don't match, Trevor, whatever you lost went into, and I just call it heat. There's a symbol for it, but I just write the word heat. A terrific example, Courtney, is skateboarding in a skate park in a half pipe. Really? Yeah. Like this. I'll bring that back in a second. So, what kind of energy have I just given our skateboarder by lifting them up? Potential. When I let them go, what will this turn into? Kinetic. Where will they have zero potential energy? At the bottom. Where will they have maximum kinetic energy? At maximum kinetic energy. Bottom. In fact, all the potential will turn into kinetic. Now, this is obvious, but here's the physics why. Where will they be going the fastest? At the bottom, because that's when they have all kinetic energy. Okay. In fact, I can even go like this and give you a lovely little bar graph. You can see, does the total energy change at all, Cohen? Nope, that's the law of conservation of energy. But you can see it gets transformed. If I'm really quick, boom, right there, all potential. Right there, all kinetic. And because energy and work are scalars, I don't care about the fact that it's a curvy path. To try and do this with some kind of vector approach would be very, very tough because the angle is changing constantly. Now, that's our magic physics world with no friction. In real life, if you skateboard and you try this, you don't just keep going back and forth, back and forth, back and forth. You lose something every time. You're running into the air with your body. You're giving some of your kinetic energy into the air molecules. There's friction between the tires and the actual skateboard itself. There's sound energy, because I can hear people skateboarding. We're going to lump all of that, John, into friction. If we turn friction on, I'm going to start off with no friction. And here's our bar graph. Where does friction tend to bleed off energy? Heat. So if you watch, I'm going to turn a little bit of friction on when Trevor's done yawning. You good? Yeah. A little bit of friction. Is the total energy changing? Is the total energy changing? No. But where are we slowly losing energy? Where are we slowly losing energy to? Which one is slowly going up constantly here? Thermal, heat. That's why you don't go as high the second time. And you don't go quite as high the third time. And you go even less high the fourth time. And eventually, all of our energy is going to be transferred into heat. This is the real world. This is the real world. This is the law of conservation of energy. Let's have a little fun. Let's build a track. Okay. Let's put a little hill here. And let's go down again. About up again, and let's just kind of smooth that out a bit. I'm going to turn friction off first of all. Bring my bar graph on. If I start this high, will I make it over the middle hill? Yes? What if I start this high? Can I make it over the middle hill? I can? Why can't I? If I start this high, then Trevor, I'll just freeze it there. That's how much energy I have. This is how much potential energy I have. To get to here, I would have to somehow gain potential energy. That violates the law of conservation of energy. If I want to make this middle hill, I have to make very certain that I start out higher than it. Like right there, I think will barely get me over. Let's see. Oh, not quite. Let's go a little higher. Hey, I made it. But Cohen, this is in our magic physics world with no friction. If I bring friction in, just a little bit even, you can see slowly heat's going up. This concept explains an awful lot about anything that you do that involves motion and changes in height. Riding a bike, skateboarding, running, all this stuff. Okay? Oh, I have here, show marble energy transfer device. Okay, pause. Courtney, my basketball player. As long as you're not adding energy to a basketball by pounding it down, then dribbling a basketball is a beautiful conservation of energy. At the top, it's all gravitational potential. Its speed for a split second at the top is how fast? 0. Its kinetic energy for a split second at the top is how much? 0. At the bottom, its potential energy is how much? 0, because it's all kinetic. Halfway down, it's half and half. Pile drivers are a great example. You raise the pile driver up to give it potential energy. Then when you let it drop, that potential energy turns into kinetic. Oh, and if it impacts something, that will apply a force over a distance. It will do work. Let's crunch some stuff. A projectile is launched straight up into the air. If its initial velocity was 84.3 meters per second, pretty fast, how high does it go? We could solve this using pre-Christmas d equals vi t plus a half at squared, vf equals vi plus at, vf squared equals vi squared plus 2. But let's try using energy. Let's say this. Ke initial plus Pe initial equals Ke final plus Pe final. By Ke, I mean a half mv initial squared. That's where the initial fits. It's the initial velocity. Potential energy is going to be mgh, and since it's initial, it will be initial. A half mv final squared plus mgh final. Are any of these 0? And what I'm really asking is, are there any times where my height is 0 or my speed is 0? Are any of these 0? Which ones? Trev?
Potential?
Which I got initial, final. When?
Oh, kinetic initial.
Kinetic initial? I think its initial velocity is 84.3. I don't think it's 0. This is not 0.
The potential energy is 0?
Oh, how high are we starting if we're launching from the ground?
On the ground?
How high as a number are we starting if we're launching on the ground? What's our height as a number?
0.
Cool. 0 times mg is just 0, vanishes, yes? Anything else? 0. VF? Oh, at the top, Trevor, for a split second, how fast you'll be going?
0.
Why? Because you've turned all of your kinetic into gravitational potential. So we really have this, a half mv initial equals mgh final. Mr. Duick, they didn't tell me the mass. No, they didn't. Wait a minute. Is there a mass in everything on the left? Is there an m in everything on the right? You know what that means? Those m's cancel. What's this question asking me to find? H final, you say. How would I get H final by itself? Divide G. H final is going to be, so there's going to be a VI squared. And what did you say I'm going to do with the G? So I'm going to put a G down there. Now, look up, folks. There is a 1/2 in front. I'm going to write the 1/2. Look up, just watch. Don't write this down, just watch. Like that. Does the 1 change anything at all? So if you're wondering, where'd the 2 come from? It came from, there's a 1/2 in front of everything. That's really a 1 on top and a 2 on the bottom, but I'm not going to write the 1. Is that okay? Trevor, what was VI?
0. Oh, no. 84.3.
Thank you. Squared over 2, 9.8. Negative 9.8, Mr. Duke, scalar. How high will this go? I'll go 363 meters. Is that right? Hopefully you're trying these on your calculator. Okay. Let's suppose this projectile was not very aerodynamic. Let's suppose you were launching, oh heck, a wadded up piece of paper. Is this, am I right? Is it 360? Yeah, okay. Let's suppose that this was not very, let's suppose you were launching a piece of paper with an initial velocity of 84.3, but you measure, it only goes 72 meters high. That means it lost most of its energy to air friction, heat. How much? So if the projectile only reaches a height of 72 meters, how much energy was lost to air friction on the way up? Or how much work did air friction do slowing the object down? Okay. Here's the law of conservation of energy. Kinetic initial, potential initial equals kinetic final, potential final. If they ever ask me to include friction or heat or something, I just go, oh, okay, I guess this time you want me to include that. If they say ignore friction, I don't write heat. It's the same situation as before, so I'm going to come back to Trevor. Trevor, are any of these zero? Oh, yeah. Quick look at money. Are any of these zero?
Potential energy initial.
Ah, because we're starting out on the ground. Anything else zero?
Potential energy final.
Potential energy final?
Kinetic energy.
Because we're not ending on the ground, we're ending up there. Okay. Because at the top, for a split second, how fast are we going? Zero. How much kinetic energy do we have? Zero. So if I hear you correctly, you're telling me it's going to be a half mv initial squared equals mgh final plus heat. Yeah, yeah? Yeah, yeah. And this question wants me to find heat. How would I get the heat by itself? How will I move that mgh final over? Subtract. You are correct, sir. I guess it's going to be a half mv initial squared, take away mgh final. That equals heat. That's how much energy we lost due to air resistance, and I'll call it air friction. Now we can be a little more accurate. You'll notice I've been avoiding air resistance like the plague because it's very difficult to calculate. And it is, but I can certainly calculate how much energy I lose to it without that much trouble. You know what? It's heat. I'll do it in red. Fiery red. 0.5. Oh, is there an M in here? Yes. Is there an M in here? Is there an M in here? This time the mass doesn't cancel. You know what? We need the mass. Did I tell you the mass in the top anywhere? I didn't. So I'm going to make a little note here. Assume, and if I gave this to you as a question, I would give you the mass, but I did this on purpose just so you realize sometimes the mass cancels, sometimes it doesn't. Assume mass equals, how about 5 kilograms? Nice round number. So it's going to be 0.5 times 5 times 83, what was it? 84.3. Squared minus 5 times 9.8 times 72. How much energy did we lose to heat?
Where did we get the mass?
I just said assume the mass is 5 kilograms. I had to tell you the mass. I wrote it right there. The question normally would tell you. Point 5 times 5 times 84.3 squared minus 5 times 9.8 times 72. You get 14,238.225 joules of heat. And heat's measured in joules. It's heat. It's energy. I'm going to go 14,200, but I'll keep that on my calculator. Cool. Or hot. John, what does part C want me to find?
Average force.
Keep going.
Okay.
Okay. Look up. What did we just find in part B?
Energy.
What type? I'm looking for a word that begins with the letter H, ends in the letter T, and has an E and an A in the middle of it.
Height. Oh.
Psst. Heat. Okay? Make a little note here. Heat is, or equals, is the work done by friction. If you want to know how much work friction did, if you know how much heat you generated, that's how much work friction did, because friction generates heat. So in part B, I said how much energy was lost due to air friction on the way up, or how much work did air friction do slowing the object down. What does part C want me to find? John, my friend?
Average force of air friction.
Well, what did I find in part B? Which is also the same as the work done by friction? What's the equation for work?
Force times.
So I'm going to argue, my friend, that the work done by friction is the force of friction times the distance that friction was acting for. You okay with that? How would I get the force of friction, because that's what part C wants me to find, by itself? I totally agree. So if I hear you correctly, you're telling me the average force. By the way, the reason it's the average force, air resistance changes depending on how fast you travel, and I didn't want to get into that, so we're just going to get an average. It's going to be the work done by friction over the distance. How much work did friction do? 14,238.225. How much distance did it do it for? 72 meters. This doesn't give us the air resistance at any one point, but it certainly allows us to calculate the average air resistance. This is about as good as we can get without calculus. 198 newtons. The law of conservation of energy says energy has to go somewhere, has to come from somewhere. It can't just magically vanish. So I wrote here, I have a very cool demonstration. I do. Next page. Where do I use the law of conservation of energy? G. So, forces, recall a free body diagram with the obvious one. Momentum, collision, explosion. So what's my trigger for conservation of energy? If I notice that there is a change in height, a change in speed, and especially if there is a yucky, curvy path, like roller coasters or ski hills, then it's a job for the law of conservation of energy. Skiing. At location Z, a 72 kilogram skier is traveling at 18 meters per second. How high up the next hill can he ski? No. Okay. Is there a change in height in this question? Yeah. As he gets higher, what will happen to his speed as he slowly coasts uphill? So, is there a change in height in this question? Is there a change in speed in this question? Is there a yucky, curvy path? This is a job for conservation of energy. KE initial plus PE initial equals KE final plus PE final. Plus heat, oh, what does it say in brackets? Ignore friction. Okay. Now I always pause and I ask, are any of these zero? What I'm really asking is, am I ever on the ground or am I ever at rest? Please come back. Are any of these zero? Am I ever on the ground? Yeah? Where? Initial or final? By the way, let's clue in. This is going to be initial. This is going to be final, right? So, which of the potential energies is zero? It's always nice, Alicia. Less work. Do I ever come to a stop? Is my kinetic energy ever zero? Where? Final or initial? Ah. Okay. What's the equation for kinetic energy? From last lesson, Ke equals a half m v, and I guess because it's initial, it'll be initial squared, equals, what's the equation for height potential energy, gravitational potential energy? That was mgh, final. Is there an m in everything on the left-hand side? Is there an m in everything on the right-hand side? So the masses do cancel. Now, Jess, they did give me the mass, but this right here, the fact that the masses cancel, this explains why grown-ups and little kids can ski together. If the masses did not cancel, then either the little kids or the grown-ups would have to constantly be adjusting their speed by changing their skis, by doing snowplow or whatever, to stay next to each other. Don't know if you ever thought about that, but there you go. What's this want me to find? Oh, hey Matt, you did this last time. How would I get the height by itself? So if I hear you correctly, you're telling me the final height is going to be the VI squared stayed where it was. What did you say I was going to divide by? And then instead of writing the 1/2, are you all okay? I'm just going to tuck a 2 down there because that's a 1/2 in disguise. In fact, it's the same equation as launching something in the air, which is kind of nice. What was VI at the bottom? 18 squared all over 2 times 9.8. It's a fraction, 2 things in the bottom, put the bottom in brackets. 16.5 meters. Now, in real life, there would be friction. Although snow is reasonably frictionless, you might get in real life 15.5 meters or something like that. But we're in our magic physics world, Haley, we're ignoring friction. Oh, turn the page? Okay. Archery. Archery is a great example of the law of conservation of energy. Suppose it takes an average force of 245 newtons to pull the bow back a distance of 68 centimeters. How much work is done in pulling back the bow? Well, work equal, what does work equal? Force times distance? Oh, did they give me a force? Did they give me a distance? Hey, Ryan, this is kind of plug and chug. Cool. 245 newtons. Am I going to put a 68 in for the distance? 0.68, yes. How much work did the archer do in pulling back the bow? 166.6. I'll write everything down. Joules. How much energy is stored in the bow? How much potential energy is stored in the bow? Put your calculator down. How much potential energy is stored in the bow? Should give me the answer right now. 166.6 joules. It's not gravitational potential energy that makes a bow or an arrow go forward. It's you've stored, I guess, elastic energy. You've stored energy in the bow. How much potential energy is stored? The potential energy in the bow now has 166.6 joules. If the arrow has a mass of 42 grams, that's 0.042 kilograms, right? How fast should it leave the bow? Jess, what's this question asking me to find? How fast? Is there a change in speed? Yeah. Is there a change in height? No. Is there a yucky curvy path? No. But is there a change in energy from potential to kinetic? This is a job for conservation of energy. So now we're extending when we use conservation of energy. It's going to look like this. Kinetic initial, potential initial. This time, though, the potential is not MGH, Courtney. It's what's stored in the bow. Kinetic final plus potential final. Are any of these 0? Are we ever at rest? Are we ever at rest? Initial or final? You let go of the string. The arrow takes off. How much potential energy is now stored in the bow? Okay. This time, though, it's not MGH. It's going to be one point, Mr. Dewick. It's going to be 166.6 joules. That equals a half mv squared. I guess V final. Is that okay, Eric? Eric, how would I get the V final by itself? What will I do with the 1? Oh, you know what? I'll ignore the 1. We've decided that. This 2, is it on the top or is it on the bottom? So how will I move the 2 over? So it's going to be 2 times 166.6. How will I move the M over? Divided by M. Now that's going to give us VF squared. Square root. These numbers are pretty accurate. I did some Google research and I'm looking at how much force it takes to draw a compound bow, distance, and what an arrow. This is a typical Olympic arrow apparently weighs about that much. 166.6. What about like a Hunger Games? I don't know. 0.042. 2 times, answer button, divided by 0.042, square root. 89 meters per second. I've seen professional archery on the Olympics. Yeah, those arrows go about across a football field in a second. That seems about right. I guess 0.1 meters per second if I want to go to 3 sig figs. Law of conservation of energy, very powerful. But it's best used for, first of all, my Nerf dart gun works very, very similarly. Where does conservation of energy work best? Oh, I got one more here. When do I get to roller coaster? Roller coasters. Okay, yeah, we're going to get there. Model airplanes. I live up by Garibaldi, and in Garibaldi, Eric. All righty. Mr. Dewick has to pause the video. As I was saying, I live up by Garibaldi High School. There's a couple of guys out there that own remote control model airplanes, and they fly them in the Garibaldi field quite often. I think one of them just now has a drone as well. So I'll watch every so it's pretty cool. So a model airplane flies horizontally at 22 meters per second. Okay. Okay. Courtney, what does A want me to find? Well, kinetic energy equals a half mv squared, 0.5. Please tell me, Courtney, did they give me the mass? What? Did they give me the speed? Oh. $484 joules of energy. Where's that energy coming from? The fuel or depending whether it's an electric plane, most of the time there's still gas motors. Okay. The plane goes into a power dive and levels off 40.5 meters closer to the Earth. How much potential energy did it lose? I think it lost mgh. I think it lost. Jaden, you with me? You're not foolishly looking at your phone or anything like that? You're good? Okay, sorry. It looked like you were trying to hide behind there. My bad. It lost 2 times 9.8 times 40.5. 2 times 9.8 times 40.5. 793.8 joules. C. Courtney, what does C want me to find? This is, and don't take this wrong, this is meant to be a no-brainer instantly. What's the answer right now? How much kinetic energy did it gain? Too slow. What? 793.8. If the energy's got to go somewhere. By the way, this explains why when planes dive down, what happens to their speed increases. Has to. Okay? 793.8 joules. Now, in real life, we would have lost some to air resistance. It's true. We're ignoring friction. Courtney, what does D want me to find? That's going to be 484 plus 793.8. $1,277.8 joules. Neglecting frictional effects, ignoring air resistance. What's its new velocity? How could I figure out how fast it's going? Well, I know it's kinetic energy. Kinetic energy is a half mv squared. How much kinetic energy does it have, Alicia? 1,277.8. Because it dove down. Has to speed up. How would I get the v by itself? Oh, Eric and I did this last time. We went, it's going to be the KE drops down. You said times by 2, divide by m, and that equals v squared. Oh, you said square root. Okay. 2 times 1,277.8 divided by, what was the mass? Oh, also 2. That's convenient. Square root. I think the 2's will cancel. Because 2 times and divide by 2 cancels. Anyways, yeah, told you. Square root. 35.7. Meters per second. I'm going to pause here, but I'm going to give you some homework. First of all, take-home quiz. We'll look at roller coasters next class. Did I mention I was at Playland yesterday for Playland? Oh, it was great. But for now, you should be able to do number 1 from lesson 4 homework. This is the skate park. Now, mechanical energy, ME, is just potential energy plus kinetic energy. Cohen, it's the total energy bar that you always saw that never changed at all. Okay? The fancy name for that is mechanical energy if it's potential plus kinetic. So you can try number 1. You can try number 2. If you're stuck on number 2, we'll look at roller coasters next class. We're going to do those. You know what? I'm just going to assign those and the quiz for now. However, I need to pause a little bit here. 1 and 2 right now. I'm going to assign the rest.